Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at the chemistry paper with you guys as you prepare for your finals. I hope that the exams have been going well so far. It would be nice to know. Just please comment below how the exams have been. Are you coping? This is, paper 2, so you're almost there. Alright, so let's have a look at question 1. So we're having a look at the prelim written in Gauteng. This should help you prepare quite well. Alright, so 1.1, the empirical formula of hexanoic acid is, and we need to choose between A and D. Okay, firstly, what is the molecular formula for hexanoic acid? Or if I were to sketch the structural formula, okay, so we need 6 carbons. And since we are dealing with an acid over here, we're expecting to have Cu, right? Yeah. Carboxylic acid. Yes, I wanted the word carboxylic. We're dealing with a carboxylic acid over here. And so we're going to then have a double bond to oxygen and a bond to OH. All right. And the rest are all your hydrogen atoms. So if we were to count, we have 6 carbons, we have 2 oxygens, and how many hydrogens? So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12. So this is the molecular formula. Okay. Now empirical formula is basically the simplified version. So if I were to get the simplest here, I would divide everything by 2. So I have O, H6, and C3. And if I look there, D would be my answer. Alright, and then 1.2. Which intermolecular forces are present between molecules of C7H15CHO? I would suggest you draw the structural formula for this so that you see what is happening. So we have 7 carbons over here. 1, 2, 3, 4, 5, 6, 7. All right, along with the hydrogens accompanying those carbon atoms. And then we have another carbon, a double bond to oxygen, and a hydrogen over there. That's the last CHO. Okay, so if you look at this clearly, it looks like it is an aldehyde. And we know that the forces between aldehydes are actually quite weak. So they have weak intermolecular forces, dipole to be exact. All right. And within those dipole, it's actually London forces as well that are there. So if you look at the options from A to D, only dipole forces, no. Dipole forces, dispersion London forces, and hydrogen forces. Well, hydrogen bonding is very strong, so you can't really have both hydrogen as well as you can't have both strong and weak. It's either strong or it's weak. Okay, so B and C we're not going to consider. So between A and D, the answer would be D. Now 1.3. So we have structures of 4 organic compounds as shown below. If we look at compound 1, it's a carboxylic acid, all right, ethanoic acid. And then compound 2, we have an alkene, we have a double bond. Okay, so ethene. Compound 3, we also have another alkene, but this time we have 3 carbon atoms, so propene. Compound 4, we have an alkane, all right, so it is propane. Okay. So now the question says, which of these compounds will decolorize bromine water faster? If it will decolorize it, we need something that can have addition reactions. Okay, so compound 4 will not work because that is an alkane. It is already saturated. So we're going to look for unsaturated compounds. And I can see that it is compound 2 and 3. All right, don't consider compound 1 just because you have a double bond. Remember, oxygen requires double bonds. Okay, so it's not like compound 2 and 3. So compound 2 and 3 are the only compounds that can allow addition reactions, and that will decolorize bromine water fast. So looking at the options, 1 and 2, no. 2 and 3, yes. 3 and 4, no. 1 and 4, no. So B is the correct answer. Then 1.4, which of the following statements best explains the role of a catalyst? Okay, it lowers the activated complex. It increases the concentration of the reactants and therefore increases the rate of the reaction. No. It provides an alternative path with lower activation energy for the reaction. Yes, that does sound correct. It does indeed provide an alternative path with lower activation energy. That is what it does. It really lowers the activation energy. And D, it increases the net activation energy. No. So C is the correct answer. It does lower the activation energy. That is the purpose of, or the role of, a catalyst. Okay, then we get to 1.5. The energy distribution curves for a fixed mass of gas at two different temperatures, T1 and T2, are shown below. T1, that's where you have a lower temperature. And how do I know? It's because if you look at the activation energy just afterwards, the area below the activation energy is very low. So it means only a few molecules are being formed, or the reaction is ongoing. So only a few particles participate in the reaction. Okay, but temperature 2 is a higher temperature. We still have the same activation energy, but the number of effective collisions has increased. It is more. Okay, so which one of the following is correct? Is the correct interpretation of the curves for the change in temperature from T1 to T2? So activation energy, that stays the same. So we look at A and D as our options. And the number of effective collisions, they have increased. Okay, so A is our answer. Then 1.6, each of the reactions represented below is at equilibrium in a closed container. In which of these reactions will an increase in pressure, okay, so we have an increase in pressure, therefore a decrease in volume, favor the formation of products? All right, so if we're looking at an increase in pressure, your volume will decrease. Therefore, we're looking at the least number of moles on the product side. On the product side. That is what we're going to do as we are looking for the answer. So A, we have more moles. Okay, firstly, we need to check, is everything a gas? It's very important. Okay, so everything is a gas. So yes, we can continue then. So A, we have more moles, number of moles on the product side. Okay, so meaning the reactants are favored. So A is out. B, again, we have more number of moles on the product side, meaning the reactants are favored. So that is out. And then C, excuse the external noise. C, we have more number of moles on the reactant side, so meaning products are favored. Okay, so C is an option. And then D, we have, well, an equal number of moles. So I don't know, we don't entertain that at all. So C, C is the one that we're going with for 1.6. And now 1.7. So consider beakers A and B as illustrated below. We have 200 cubic centimeters, so that's the volume, of 0.25 mole per cubic decimeters, that's the concentration of sodium hydroxide for beaker A. And beaker B, we have 150 cubic centimeters of 0.1 mole per cubic decimeters of sodium hydroxide. Okay, so now 20 cubic centimeters of the sodium hydroxide solution in beaker A is added to the sodium hydroxide solution in beaker B. Which of the following represents the correct calculation for the new concentration of sodium ions in beaker B? So I hope you see that we can agree that the volume now in beaker B will actually be 20 plus the 150. So we have 170 cubic centimeters, which is 0.17 cubic decimeters. Okay, so the options that I'm seeing here from A to D, only A and B we're going to look at. Okay, so that's the volume part. And remember, concentration is number of moles over volume. So now let us get the number of moles for A and the number of moles for B. Okay, because we're going to add those. So far we have the volume. Now let's deal with the number of moles. So for A, the number of moles there, remember number of moles is concentration times volume. So we have 0.25, that's the concentration, and the volume is 0.2. And then for B, we have 0.1 moles per cubic decimeters multiplied by 0.15 cubic centimeters. So let's just calculate that. Okay, so we have 0.25 multiplied by 0.2, and we get, okay, we get 0.505. Okay, am I multiplying this correctly? Yeah, 0.25 mole per cubic decimeters times 0.2, I get 0.05, and then 0.1 times 0.15, that is 0.015. Okay, actually, I think, no, sorry. So we took 20 cubic centimeters, not 200. Not 200. So that would be 0.02. Okay, 20 divided by 1,000 is 0.02. So 0.25 multiplied by 0.02, and that is 0.005. Okay, because, yeah, we're looking at the portion that was taken to beaker B. Okay, so yes, actually, let me do it like this. Okay. In beaker A, so number of moles in beaker A is 0.05, but the ones that were transferred, so the 20 cubic centimeters that were transferred to B, it's actually going to be 0.25 multiplied by 0.02, and that is 0.005. Okay, so yes, number of moles in A is 0.05, number of moles in B is 0.015 plus the 0.005. Okay, I hope I didn't confuse you there. I hope it makes sense, but yes, that is for A, and that is what was transferred to B. So if we look at the answers between A and B, very close. I almost went with B, but this is for beaker A. Okay, so A is the correct answer then, because we look at what we transfer to B only. We're not considering A. So it's going to be 0.015 plus 0.005. All right, 1.8. When a galvanic or voltaic cell delivers current, the purpose of the salt bridge is to... Okay, so remember the salt bridge has quite a few functions. Okay, so it basically provides, or rather it contains an electrolyte, right, which provides electrical contact between two solutions. So basically the salt bridge, it completes the circuit. It keeps the two electrolyte in the two half cells separate so that they do not mix. Okay, it allows movements of ions between the electrolytes, so that we have electrical neutrality. There are quite a few things. Okay. So if we have a look at the options that they give us, it allows electrons to move in the cell. That's too vague. Ensures electrical neutrality in the cell. Yes, that it does. It's actually the major thing that it does. It prevents two solutions from mixing. I think it needs to be more specific. Rather, it should have the statement should have said it keeps two electrolytes in the two half cells separate. Okay, allows electrons to travel from the cathode to the anode. Actually B is the answer that would go with. It ensures electrical neutrality in the cell. And then 1,9. Which of the following metals is the strongest reducing agent? Okay, strongest reducing agent. I'm just going to write them down so that we can go have a look at the table. Most of you prefer table B, 4B. So I'll use that one. Okay, so basically you can see this arrow on the right hand side says increasing reducing ability. So that is what we're going to look at. All right, the one that is highest on this from the top going down. So the one that is highest in this table is the one that we're looking for. Okay, so silver, zinc, copper, aluminium. Let's see which one we find first. So I see aluminium is first. So that's the strongest. Then we get to, so there's zinc, there's copper. Let's see. So zinc is the second strongest reducing agent. And then we get to copper. Yes, copper is number 3. And silver is probably down. Silver is here at the bottom. Okay. So we can see that aluminium is the correct answer. Okay, so let's just go back to our... Okay, so which of the following metals is the strongest reducing agent? Aluminium is the strongest. Okay. Which one would be the strongest oxidizing agent? It would be silver. And then 1.10. Gaseous chlorine used to disinfect the water in public swimming pools reacts with water according to the following balanced equation. So we have chlorine gas plus liquid water is equal to HOCl plus HCl. Okay, hydrogen chloride. The addition of chlorine changes the pH of water in swimming pools. Okay, so we can see in this equation HCl is more acidic. So which of the following substances must be added to public swimming pools periodically to increase the pH? We do not want acidic pool water. It will burn your skin. Nor do we want very basic. It also can burn. So we want it to be more neutral. So since already it is acidic, we need a base to neutralize it. So option A, we have ammonium chloride. Ammonium is a weak acid, so we don't want to add more acids, right? B, you have sodium carbonate. So carbonate is a base, so B is an option. C, we have potassium chloride. No, I wouldn't really add potassium chloride to it. And then, D, definitely not. That is sulfuric acid. That is a very strong acid. It will definitely make it more acidic. So yeah, what about the potassium chloride? Is it more on the acidic side or is it more on the basic side? But yeah, what I would then choose is basically the sodium carbonate. Even though the carbonate is more of a weak base, I think it's fine. I think the acids that you have in the original formula is HCl is quite strong, but that's the base that we have. So potassium chloride is more of a salt, all right? So it's more neutral rather than it being a base or an acid. Okay, so the only base that we really have is B here. So B would be the correct answer that we go with, and that would conclude question 1. question 2, and we're having a look at organic compounds. Please don't forget to like our videos and also subscribe to our channel. Alright, so A to F in the table below represents 6 organic compounds. I think let us just discuss firstly what those compounds are, and hopefully that will help us to answer the questions quite quickly. So for A, I see that I have an OH group, so I must be dealing with an alcohol. And what is it? 1, 2, 3, 4. So it's butanol. But on which carbon is this OH group on? It's on the second carbon, right? So it is going to be butan-2-ol, but there's also a methyl group on the very same second carbon. Okay, so when we name it, it will be on the second carbon, we have a methyl group. So 2-methyl and butan-2-ol, or 2-butanol. Okay. And then B, we have pentan-3-one. Okay, so we have a ketone. We have 5 carbons. And on the third one, that's where we have our double bond to oxygen. All right, so that's our ketone. So if I were to have the structural formula, it would look like this. I'm not going to put in the hydrogens at this point. And then now we have methyl butanoate. So this is an ester. Okay, you initially had methanol. Okay, and then you also had butanoic acid. All right, so 1, 2, 3. And for a ester, or for an ester to form, you take out the H2O. So basically, you are left with, look at me forgetting the oxygen there. So you have your oxygen, and then you have your carbon, double bonded to oxygen, and you have the rest of your carbons. Okay, so there should be 5. There should be 5 carbon atoms there all together. Okay, and 2 oxygen atoms, and the rest will be hydrogen. Okay, so that's C. And then D, I see that we have a carboxylic acid. Let me look at the longest chain, 1, 2, 3, 4. So it is butanoic acid. All right, so yeah, butanoic acid. Let me just see, 1, 2, 3, 4. But also on the first carbon, we have a methyl group. Okay, so what? We can say 1-methyl butanoic acid. All right, and then E. So here I see we have a double bond to oxygen, and it's not at the end, it's somewhere in the middle. So we have another ketone. It's not an aldehyde. So yeah, 1, 2, 3, 4, 5. So it's still pentan, but 2-one. Okay, pentan 2-one. And then lastly, F. So this looks like it is an alkane. We have 1, 2 plus 3. We have 5 carbon atoms. So it could be, this would be the structural formula. Okay, it's just a normal alkane. So with 5, so it's pentane. Okay, so we at least know more or less what we have, and let us hope that the questions will go by smoothly. So how many minutes are we allocating to this? We are allocating 18 minutes, and how many have I taken? So that you can see, is it worth doing this in an exam? So that's almost 5 minutes. Okay, let's see if this will go quick. So it says consider the organic compound A. A, which we said it's a 2-methyl-butane-2-ol. Is it a primary, secondary, or tertiary alcohol? Give a reason for your answer. So you can see that the alcohol group is on the second carbon. Or rather, if you want to look at it, you can say the OH group, the carbon that the OH group is attached to, is also attached to 3 other carbons. So this is a tertiary alcohol. Okay, that's how you actually determine whether it's a primary, secondary, or tertiary alcohol. And why is it a tertiary alcohol? Because OH's carbon is attached to 3 other carbons. Okay, 3 other carbons. All right, and then 2.1.2. Write down the IUPAC name for the above mentioned compound. So we've already done that. All right, so we said on the second carbon, we have a methyl group, so 2-methyl. And again on the second carbon, we have the OH group, so 2-methyl-butane-2-ol. 2.1.3. The above mentioned compound undergoes an elimination reaction. Write down the structural formula of the major product that is formed. Okay, so basically, if we just rewrite the structural formula or redraw the structural formula. Okay, if this undergoes elimination, we're basically going to form a double bond. All right, and we need to ensure that as we form that double bond, we have a major product. Remember, there can be a major product or a minor product. And here we're going to apply Zaytev's rule. Okay, so if more than one elimination product is possible, let me just number the carbons. Okay, so if more than one elimination is possible, then if we want to form a major product, we will do that, né? And by doing that, the major product is formed when the H atom is removed from the C atom with the least amount of hydrogen atoms. Okay, so if I look between carbon 2 and carbon 3, carbon 2 doesn't even have H atoms. So actually that's where the double bond will form. Carbon 3 has 2 H atoms. The carbons at the end have 3 H atoms, so we're not even going to consider those. So the double bond basically forms on the second carbon. And since it forms on the second carbon, we need to eliminate. Okay, so in between C3 and C2, we're going to put, let's just do that. We're going to have a double bond over here, and that means we're left with 1 of the carbons. But the double bond does form on carbon number 2. All right, and basically that's what they wanted, the structural formula. Now we can go over to 2.2. It says consider the organic compound B. So that's pentane 3-O, that's our ketone with double bond to oxygen on the third carbon. So it says 2.2.1. Define the term functional isomer. Okay, so if you know what an isomer is, remember an isomer, we have organic compounds that have the same molecular formula, right? And if it's a functional isomer, it means that while it has the same molecular formula, it is in different functional groups. Okay, let me just summarize. So same molecular formula, but different functional groups. And then 2.2.2, write down the homologous or homologous pronunciation. So write down the homologous series to which the above mentioned compound belongs. All right, so this is definitely a ketone. And 2.2.3, write down the IUPAC name of its functional isomer. So remember, ketones are functional isomers with aldehydes. All right, so with an aldehyde, if you have, and aldehydes are straightforward because the double bond to oxygen is at the end, so you don't even need to write out a position of where the double bond to oxygen is. So if we have pentan 3-one for the ketone, what will the aldehyde be? It will simply be pentanol, okay, with the Al at the end to signify that it's an aldehyde. And then 2.2.4, write down the letter that represents its positional isomer. Do we have aldehydes here? Let's see. E, actually, we made it a ketone. So letter represents, oh, positional isomer, yes. I'm thinking functional isomer. So 2.2.4, the letter that represents its positional isomer, it has to be E, because if B is pentan 3-one, E is pentan 2-one. The position of the oxygen atom has moved. All right, so E is the one. Okay, so this is going pretty nicely, quickly. And then it says for 2.3, write down the balanced equation using molecular formulae for the complete combustion of compound F. Remember, compound F is pentane, okay? And the molecular formula for pentane, we basically have C5H. Remember, for alkanes, we have 2N plus 2. So 2 times 5 is 10 plus 2, that is 12. And then it's complete combustion. So if you are combusting something, you add oxygen to it, right? And then what would the results be? With combustion, your results, you always have carbon dioxide and water as your products. Now we need to go and balance, okay, because we have 5 carbons over here. So we just need to put a 5 there. And then, okay, let me just do this. We have 5. And then our hydrogens are 12. And then our oxygens, we have 2 of them. Okay, here we just equalized it, so we put 5 carbons. And then our oxygens, well, we have 10 over here plus the 1 there. So, so if we have 10, but let's look at the hydrogens. Here we have 12 hydrogens, right? So there we have 2. So I think we're going to put a 6 over here. We start first by balancing the hydrogens before we get to the oxygens. So yeah, now we have 12 hydrogens. And how many oxygens do we have? So we had 10 plus 6. So we have 16. So what times 2 gives us 16? 8. I think that is balanced. Yes, now we have 16 and we have 16 over here as well. So everything looks balanced, and we have our balanced formula, so we can just erase all the working out. And are we done with question 2, or is there still some more? We are done. See you in question. Question 3. 3 structural isomers with molecular formula C6H14 are used to investigate the effect of branching on the physical properties of hydrocarbons. So we have alkanes here, all right, and I see that because of C6H14. All right, so basically we have hydrocarbon A, B, and C. A is the least branched, it only has a branch on the second carbon. B has a branch on the second and the third carbon, and C has branches on the second carbon. Okay, and then the results obtained for the first 2 investigations are shown in the table below. So we have melting point as well as boiling point for all the hydrocarbons, right, from A to C, and we see that A has the least melting point, yet the highest boiling point, which is you would expect that the more straight or less branched a hydrocarbon is, the higher the boiling point. And normally boiling point and melting point go together. So higher boiling point, higher melting point. But in this case, it's quite different. I wonder why. Okay, C on the other hand has the highest melting point, yet the least boiling point of the three. So they're doing opposites here, which is something really that I'm not used to seeing. But let's answer the questions that follow. So 3.1, it says define the term melting point. Okay, so please, it's melting point, not melting. So don't say where solid phase goes into a liquid phase. This is melting point. And the melting point is basically the temperature at which the solid and liquid phases of a substance are at equilibrium. Okay. And 3.2, write down the independent variable for this investigation. By independent variable, it means if I were to plot this on a graph, okay, independent would be what is on the x-axis, all right? Dependent is what is on the y-axis. So if I were looking at this, for investigation 1, we have melting point, right? The melting point is dependent on the structure of the hydrocarbon. Okay, so basically the structure here, we're looking at branched. Yes, we're looking at the effect of branching. All right, so I would say on the independent variable, I would either put branching. Okay, or maybe we could even look at chain length, because the more branches there are, the less the chain length will be. All right, whereas on your dependent axis or your dependent variable would be melting point, because that is for investigation 1. Okay, so yeah, but anyway, they just wanted for the independent variable, so I would say branching or chain length. Now 3.3, it says explain why these 3 organic compounds are called structural isomers. Now remember what an isomer is. It is basically molecules that have the same molecular formula. Okay, so that is just isomer. Now when we go to structural isomer, it just means that they have the same molecular formula but different structural formula. So that is what I would say. So same molecular formula but different structural formula. Okay, so yes, because the structure keeps changing, but at the end of the day, it has the same molecular formula, which is C6H14. Now 3.4, write down the type of intermolecular forces present between molecules of these isomers. All right, so there are two, when it comes to organic compounds, two distinct intermolecular forces present. All right, you either have the strong hydrogen bonding, which we find in carboxylic acids and alcohols, or you have your weak intermolecular forces like your London forces, your dipole-dipole or dipole-induced dipole forces. All right, so in this case, we're dealing with hydrocarbons here, so they are the weak intermolecular forces, and the type that I would address here, I would probably put the London forces, and it's only 1 mark, so yeah. Then 3.5, explain the difference in melting points between molecules A and B. All right, so between A and B, let's talk about the melting point, and then we'll discuss why that is. Okay, so the melting point of A, which I would expect to be the highest, but in this case it is the lowest. So A has the lower melting point than B, all right, whereas B, sorry guys, I'm recording with a friend here. Yeah, and then B has a higher melting point than A. Okay, and we're probably going to have to look at why that is the case, because it doesn't make sense. The more straight or the longer the chain, the higher the melting point should be. The more branched it is, the less the melting point should be. But in this case, that's not the case. It's showing something different. So that's what we are seeing, first of all, with the melting points, that A has a lower melting point than B, all right? And B has a higher melting point than A. Now let's talk about the structure. Okay. So the structure for A is less branched. Okay. Or you could say it is less spherical. Whereas with B, it is more branched. It has branches on the second and the third carbon, whereas A has only has a branch on carbon number 2. Okay, so it is more branched. All right, after talking about the structure, I think let's have or compare the strength of intermolecular forces. Okay, because if A has a lower melting point than B, it means that the intermolecular forces are actually weak, which doesn't make sense, but that's what we're observing. So basically, hydrocarbon A has weaker intermolecular forces than B, and B, in this case, since it has a higher melting point, it basically has stronger intermolecular forces. All right, and if we were to also look at the energy needed to overcome the intermolecular forces, we could say because A has a lower melting point, it means that it has weaker intermolecular forces, therefore we need less energy. Okay, so less energy is required or needed to overcome the intermolecular forces. Okay, but B, because it has a higher melting point than A and it has a stronger intermolecular forces, it means that more energy is required. Okay, more energy is required or needed to overcome the intermolecular forces. Like I said, guys, this is really unexpected. I was expecting hydrocarbon A to have a higher melting point, like it has the higher boiling point, but this is what it is. Okay, and now for investigation 3. So 1 was melting point, 2 was boiling point, and 3 now is the vapor pressure. Okay, measured at 25 degrees Celsius. All right, so we can see now, here's the thing that I'm expecting. If a hydrocarbon has a higher boiling point, I'm expecting it to have a higher melting point, but it should have the lowest vapor pressure. Okay, that is the trend I'm expecting to see. So yeah, there we are given vapor pressures, and now let's read the question below. So it says, using the information of investigation 2 and investigation 3. Let me take a break. All right, where were we? 3.6. Okay, so yeah, let's switch this off. So 3.6, it says, using the information of investigation 2 and investigation 3, match the correct vapor pressure with the appropriate molecule. Write down the letters A to C below each other with the corresponding vapor pressure next to each other. So A, remember, it had the highest boiling point, so it had the lowest vapor pressure. Okay, so you have 211. Okay, and the next one would be 235, and the last one 319. Okay, let me just write them down. Let me not. Alrighty. Okay, and then 3.7, the last question, it says, Fully explain the answer in question 3.6. Well, basically, the higher the boiling point, the lower the vapor pressure will be. Okay, so we saw that the boiling point of A is higher than the boiling point of B, and the boiling point of B is higher than that of C. All right, and as a result, we're expecting that with the highest boiling point will be the lowest vapor pressure. Okay, so that is it, and we are done with question 3. Question 4. This is the last of the organic chemistry. We'll be dealing with organic reactions. So it says the flow diagram below shows how ethene can be used to prepare various organic compounds. The letters A to F represent different organic reactions. Alright, so I suggest we have a look at all of these reactions, make sense of this diagram, flow diagram, and hopefully answering questions will be much quicker. Alright, will be much quicker. So let's just see how much this is out of. This is a very loaded question. It's out of 22 marks. So if I say 22 multiplied by 1.2, we should be spending about 26.5 minutes. Alrighty, so let's see, we're already just under a minute. Let's see how far we get with this. I want to start with bromoethane. Okay, so we have bromoethane. I'm glad that we're dealing with only 2 carbon atoms. Makes life a little bit easy. So on one of the carbons, you'll have a bromine atom. All right, I'm not going to put in the hydrogen atoms there. And then we go over to ethene. So ethene, double bond. Okay, and then we have our hydrogens there. Then we go over to CH3, CH2OH. That looks like ethanol because we still have 2 carbon atoms. All right, so we have OH over there, and that is our, let me just write it down. This is ethene, this is ethanol, and then we have with us compound X. All right, but before we get to compound X, I see we have a carboxylic acid. Okay, as long as you see Cu, just know that you have a carboxylic acid. And with that carboxylic acid, I'm going to put it next to the alcohol because I'm seeing here that if we have alcohol and we have a carboxylic acid, compound X should be an ester. All right, so I'm going to put the carbon there with a double bond to oxygen, and we have OH. All right, and then next to it we have 3 carbon atoms, and then we have the last carbon atom with its 3 hydrogens. All right, and this carboxylic acid, we have 5 carbon atoms, so we have pentanoic acid. All right, and then all of that produces an ester. Okay, so compound X, which is an ester. Do you know what ester it is? If you want to know what would form an ester, take out water. Okay, once you take water out, let's use a different color. Once you take the water out, this will be your ester. You have oxygen, double bond to oxygen, 1, 2, okay. Right, so we have 1, 2, 3, 4, 5. Okay, and what would its name be? So we have ethanol, so the first part would be ethyl or ethyl. and then you have your 5 carbons, so ethyl or ethyl pentanoate. Okay, so we've named the compounds. All right, now let's look at the reactions. So when we go from bromoethane, okay, that is a haloalkane. All right, if we go from haloalkane all the way to an ethene, we are basically eliminating. Okay, so F would be an elimination reaction. Okay, this is where F is. Yeah, basically we are eliminating. So elimination reaction. And what kind? We are basically taking out hydrogen bromide. Okay, and if we look at an elimination reaction where we take out a haloalkane, basically, no, not a haloalkane, taking out a hydrogen, one hydrogen and one halogen. Okay, so basically if we are eliminating that, we can say we are dehydrohalogenating it. So it's an elimination reaction. If you want to be very specific, it's basically dehydro, because we're taking out a hydrogen, so dehydrohalogenation. We're taking out a hydrogen, we're taking out a halogen, so dehydrohalogenation. Okay, and then if we look at the opposite, now we're going from an alkene to a halogen or haloalkane. Okay, so we're gonna add something to it. So reaction C would be an addition reaction. Okay, we are basically adding a hydrogen and a halogen, so that would basically be hydrohalogenation. Okay, hydrohalogenation. Okay, and with the hydrohalogenation, we don't really need a catalyst, but for dehydrohalogenation, we basically need a concentrated strong base. Okay, or basically heat, okay, to make this reaction possible. So a concentrated strong base like sodium hydroxide, that would do. All right, now I see there's a reaction from bromoethane to our alcohol ethanol. All right, and there it's D. So we see that we went from a bromoethane to ethanol. That looks like it would be a substitution because we have single bonds there. So D would be substitution. And what kind of a substitution reaction? All right, I'm glad you asked. Well, basically, we are substituting our hydrogen bromide with water. Okay, yeah, either we do it with water, or we do it with sodium hydroxide. So we don't really know, but all I know is at the end our product will be alcohol, and if we did it with water, it would be alcohol and a hydrogen with a halogen. Okay, or if we did it with sodium hydroxide, it would be alcohol with the sodium and the halogen. Okay, so we don't know. We really don't know. But basically, that's a substitution reaction called hydrolysis. All right, then let's look at A. So basically, we go from our ethene to alcohol. That should be an addition reaction. And what kind of addition reaction? Basically, we are hydrating it. Okay, so A, it's an addition reaction. specifically hydration. All right, and are there any reaction conditions there? Well, basically here you need concentrated sulfuric acid. Okay, so now let's look at B. So if we go from our alcohol to our ethene, we are basically dehydrating it. Okay, and that reaction there, dehydration, is elimination. All right, so B, we have our elimination reaction. This elimination reaction basically will be dehydration because we're taking out the water. We are dehydrating it, dehydration. Okay, and for dehydration, what do we need? So again, with hydration as well as dehydration, you need concentrated sulfuric acid. Concentrated sulfuric acid or heat. Okay, so that's B, and lastly, E. Alrighty, so there where we are forming an ester, we have E. And basically E, we can say it is esterification. Okay, but if you want to get all technical, you could say, let me just write there, esterification is easy to remember because you can see that an ester has been formed. So esterification, or you could say it is condensation. The more formal term would be acid catalyzed condensation. But I know I wouldn't remember that in an exam. I would remember esterification. It's a nice term. And like the the acid catalyzed condensation. Okay, so yeah, those are basically the reactions that have formed. And we have taken how many minutes there? 11 minutes? My goodness. Just to break it down. And now hopefully the questions that we're going to answer will go by very quickly. Okay, so we have like how many minutes left? We have 15 minutes left. Okay, so 4.1, it says identify the type of reaction represented by B. Ooh. Okay, I'm recording here with my friend. All right, so for B, we've already spoken about it. It's an elimination reaction. If you wanted to be specific, we would say dehydration. And for D, we said it's substitution reaction, or you could say hydrolysis. All right, and then 4.2, it says write down 2 reaction conditions for reaction B. Okay, so we said we need concentrated sulfuric acid, or heat. All right, 4.3.1. For reaction A, okay, that's our addition reaction, the hydration. It says write down the name of the inorganic reactant. Okay, reaction A, addition, where we have hydration. Remember hydration, we have water there. Okay, so name the inorganic reactant. That's basically H2O, or you could have written it down, water. All right, and then 4.3.2. Okay, this is going by quite nicely and fast. It says write down the chemical formula of the catalyst needed. So we said we needed concentrated sulfuric acid. Okay, concentrated sulfuric acid, because they wanted the chemical formula of the catalyst required. All right, now 4.4.1, for reaction C, what happened with C? We have an addition reaction, hydrohalogenation. Okay, so use structural formulae and write down a balanced chemical equation. Okay, so this is now for reaction C. We're going from ethene. Okay, we already sketched out how ethene looks like, but please this time put the H atoms, hydrogen atoms. So we have ethene there, and remember we are adding, remember from bromoethane to ethene we eliminated hydrogen bromide, but the reverse is adding hydrogen bromide. Okay, did they want structural formulae? Yes, so we're going to put H and a line, Br. Please don't just write HBr. you need to put structural, put it as a structure there. Okay, and what it's going to give us, bromoethane, right? So we have our 2 carbons. Let's see how I drew it. Put the bromo there. It doesn't matter really where you put it. The bromine. Okay. Yeah, is that it? Balanced chemical equation. Is it balanced? We have 2, 4, 5 hydrogens there. 2, 4, 5. Yes, 1 bromine, 2 carbons. It's balanced. It's all good. Alrighty, and now 4.4.2. It says explain why no water should be present during this reaction. Why do we not want any water over there? Okay, well, if we were to have water, remember what happened to bromoethane for reaction D, where we have hydrolysis. If you were to have water, it just might turn into alcohol. Okay, so explain why no water should be present. We're trying to avoid the formation of an alcohol. Okay, we don't want any alcohol present there. All right, cool. Now 4.5. Reaction E represents the conversion of the alcohol into organic compound X. Okay, so we have an alcohol, and added to it is a carboxylic acid. So we already discussed that compound X is an ester. Okay, so 4.5.1, the type of reaction is esterification, the nice uncommon term, or you could have said condensation, acid catalyzed condensation if you may. All right, and then 4.5.2, write down the chemical formula of the catalyst needed. So what catalyst do we need there? Yet again, concentrated sulfuric acid. All right, and then remember, please put it like this, H2SO4. Don't write down sulfuric acid because they wanted the chemical formula. They even put it in bold. And 4.5.3 says write down the structural formula of compound X. We already did it. So yeah, it's a matter of just copying down what we did. Remember, we had ethanol to begin with, so 2 carbon atoms. Then we bonded to oxygen, then we have that carbon bonded to oxygen, and this should be 4 extra carbons because it is ethyl or ethyl pentanoate. So 1, 2, 3, 4, 5. Okay, and then we just put in our hydrogen atoms over there. Please do not leave them out. All right, there we go. All right, and that is it. Now 4.5.4. The IUPAC name for compound X, we already wrote that down. So it's ethyl or ethyl pentanoate. We are flowing, guys. We are flowing. 4.6. Now it says reaction F takes place in the presence of warm, concentrated sodium hydroxide. Now use condensed structural formulae and write down a balanced equation for the reaction. Remember, F is when we go from bromoethane all the way to ethene, and we said it's an elimination reaction or dehydrohalogenation if you may. And we said there we needed heat or concentrated sodium hydroxide. Okay, and there they told us about concentrated sodium hydroxide. Now we're going to have to use condensed structural formulae to write down a balanced equation. Okay, so depending on how you did it, so condensed, let's just start with CH3. Okay, if I'm going to look at this bromoethane. Okay, so we're going to start with bromoethane, and it has to be condensed. So CH3, and then we have CH2, and our bromine, we always write that bromine at the end. Okay, and then we have this presence of concentrated sodium hydroxide, so NaOH. And what do we get as a result? Let me just remove this. So we're going to get ethene. So ethene, remember, it's just 2 carbon atoms and 4 hydrogen atoms. So we have CH2, and remember, hydrogen and bromine were eliminated. So if you have hydrogen and bromine that were eliminated, the hydrogen tends to go to the OH, and the bromine tends to now mix with sodium. So you're going to have sodium bromine as one of the products, as well as water. Okay, so that would be our condensed structural formula, and this is for 3 marks. And is it balanced? Yes, it is, because I see 6 hydrogens, 5, 6, yes, 1 bromine, 1 sodium, and 1 oxygen. So it is balanced. Now 4.7, large straight chained alkanes can be catalytically cracked to produce shorter chained alkenes and branched alkanes, which are more suitable for use in petrol. The reaction below indicates the catalytic cracking of octane. Okay, so we have octane and it cracks, so now we have ethane, CH2, plus compound Y. Okay, so let's see, how much time do we have? Okay, we still have some time, 21 minutes. So I'm going to just write down the structural formula of this octane. All right, so we have 8 carbons, 3, 4, 5, 6, 7, 8, and they are our hydrogens. I'm not going to put the hydrogens down. And then after cracking, you have, okay, so there we have our ethene, and then a compound Y. So basically whatever is left behind. So you're going to have 6, what do you call that? You're going to have 6 carbons. Okay, and remember your compound will always be, like they said here, you would have either maybe a branched alkane, but you'll have, the product will be shorter chained alkenes. So we already have our alkene, branched alkanes. Okay, so compound Y, I'm expecting it to be an alkane. So if I've already used 2 carbons, what will be remaining is 6 carbons. Okay, and because it's an alkane, we're going to have 2n plus 2. So 2 times 6 is 12 plus 2 is 14. All right, so when it says 4.7.1, write down the IUPAC name of compound Y. That's basically going to be hexane. Okay, that's just a straight chain, but if you wanted to put some branched, branches to it, as long as the molecular formula ends up being C6H14, I think that is fine. But there's so much room for branched alkanes that you can put. I don't want to even go there, so I'll just stick to hexane. And then lastly, are we there? Yes. It says briefly explain why shorter chained alkenes and branched alkanes are more suitable for use in petrol than large straight chained alkanes. So this is where you look at your theory concerning cracking, all right, and give a reason for it. So basically, in shorter chained alkenes and branched alkanes, the surface area is less. Okay, so that's the first thing. We have surface area that is less. All right, and if the surface area is less, it means that your intermolecular forces are actually weaker. All right, and therefore, if you have weak intermolecular forces, it means that when it comes to energy, you need less activation energy. Okay. Yeah. So, I mean, you don't want, with the use of petrol, you don't want to have strong intermolecular forces, therefore requiring a high activation energy. Then petrol would be more expensive than it is right now. Okay, so yeah, we need shorter chained because shorter chained alkenes and branched alkanes because the surface area is less. As a result, you have weaker intermolecular forces, and as a result, you need less activation energy, and it makes it more flammable. How many marks is this? 2 marks, yeah. Any 2 that you're given. So it makes it more flammable, all right. And yeah, I think that's where we're gonna end this, all right. So we needed, 26 minutes, and we are at 25. So that worked out quite perfectly. I don't know how you normally attempt these questions. Maybe you just go straight for it, but I prefer just analyzing it initially, and then it flows from there. Okay. Question 5. Just a reminder, please don't forget to like our videos and also subscribe to our channel. So it reads as following. The following apparatus was used by a group of learners in an investigation to find out how surface area affects the rate of reaction between excess solid magnesium ribbon and dilute nitric acid with a concentration of 0.05 mole per cubic decimeters. So during the reaction, the gas formed is collected in the measuring cylinder. The balanced equation for the reaction is given, and the summary of the investigation is tabulated below. So experiment 1 is when the ribbon was cut into 5 small pieces. Experiment 2 is just the ribbon as one large piece, and the mass was 2 grams. Okay, so they kept the mass constant. Now the results for experiment 1 are plotted on the graph below. All right, so obviously experiment 1, as you cut the ribbon in 5 small pieces, the surface area has increased compared to experiment 2, which has 1 large piece. Okay, and one of the factors for the rate of reaction is that if your surface area has increased, the rate of the reaction will also be faster. Okay, now 5.1. Besides the mass and the volume of the reactants, give one other variable that must be kept constant during this investigation. All right, I would say one of the factors which affect the rate of reaction that is almost always mentioned would be temperature. Okay, so remember the rates or the factors that affect the rate of reaction would be the nature of the reactants. In this case, we have magnesium. It would be the concentration. That's if you're dealing with gases and aqueous solution. It would be pressure if you're dealing with gases. Surface area is what we're looking at the moment, temperature as well as catalyst. So name one of them. So in this case, really, I would go with temperature. Alrighty, and then 5.2, write down the dependent variable in this investigation. If I look at this graph, dependent variables are on the y-axis, whereas independent is on the x-axis. So in this case, our dependent variable would be the volume of gas produced. But it's quite important for you to say the volume of gas produced per unit time, okay? Because we are really looking at the rate at which things are done here. In this case, yeah, the rate at which the volume was produced. So you could say volume of gas produced per unit time. Or simply put, really, rate of reaction. That is the dependent variable. Okay. And then 5.3, use the graph to calculate the average rate of the reaction between 2 and 2.5 minutes. I hope you see that the time given to us is in seconds. Okay, so 2 minutes will just be equal to 120 seconds, and 2.5 minutes, I'm just going to calculate that quickly. So 2.5 times 60, so that is 150 seconds. All right, so I'm going to go and look at 150 seconds. So if I make that a bit bigger, 150 seconds, I'm getting a volume produced to be 48. Okay, 48 cubic centimeters. And then for 120, it is 42. Okay, so let us now put that all in a put it properly. So the average rate of reaction would be equal to change in volume over change in time. So we have 48 minus 42. Okay, that's cubic centimeters. And then we have 150 minus 120, and that is seconds. So they didn't actually tell us which unit to use. So, oh, they did. In cubic centimeters per second. Okay, that's great. If they had said cubic decimeters, you'd have to convert from cubic centimeters, or whatever it is that they asked. But at least we don't have to convert anything at this point. So we have 48 minus 42 divided by 150 minus 120. 120. Okay. So that is 1/5, which is simply 0.2. So 0.2 cubic centimeters per second. Okay, awesome. And that was our 3 marks. Now 5.4. It says, will the rate of the reaction at 250 seconds be greater than, less than, or equal to the rate calculated in 5.3? All right, so if we look at the rate calculated at 5.3, between 120 and 150 seconds, the slope there is quite steep. Okay, if you have a look at 250 seconds, it's starting to flatten out a bit. So the rate at 250 will actually be less than. Okay, it will be less than the rate calculated in question 5.3. Now, if we were to give a reason for our answer, again, like I said, the gradient is less steep at 250 seconds. Okay, so at 250 seconds, the gradient is less steep. Let me not use m. Let me just write it down. So at 250 seconds, the gradient is less steep, okay, than compared to the one at 120 seconds or even 150 seconds. Okay, so yeah, so as the gradient is less steep, that means that you have a decreased reaction rate. Okay, if it was more steep, then your rate of reaction would actually be increased. Decreased rate of reaction. Alrighty, and then 5.5. Predict how the gradient of the graph for experiment 2 will compare to the Predict how the gradient of the graph for experiment 2 will compare to that of experiment 1. Okay, so like I said initially, if it is one large piece, the surface area is not that big, and as a result, it would be, the rate of reaction would be less. Okay, and if the rate of reaction would be less, we're expecting the gradient of the graph to actually decrease. Okay, so they didn't really ask for a reason, but it will definitely decrease. Now 5.6, calculate the mass of magnesium metal that remains in the conical flask when the reaction has stopped, assuming that the molar volume is 24 cubic decimeters per mole at room temperature. Alright, so I would like for us to have a look at the formula that deals with molar volume. So you have number of mole equal to the volume over the molar volume. Alright, and getting back to this. Okay, so now for the mass of magnesium that remains when the reaction has stopped. When the reaction has stopped, I hope you see, that's where the flat line is on the graph. So basically, we have a volume of gas that is produced to be 60 cubic centimeters. Okay, so we have a volume of 60 cubic centimeters. If we convert that to cubic decimeters, we will get 0.06. Okay, because we divide that by 1,000. All right, and we need to convert it to cubic decimeters because the molar volume is in terms of cubic decimeters per mole. All right, so now we're trying to find the number of moles for hydrogen that is produced. Okay, so that will be equal to the volume, which we determined it to be 0.06 over the molar volume, which is 24. So let's just calculate and see what that is equal to. Ooh, this little one is busy. Okay, baby girl. All right, so that is basically 0.0025. Okay, and what is the unit for that? Well, we're looking for the number of moles, so it's basically mole. Alrighty, and then what do we do next? Then we're going to look at the equation and see the number of mole. If we have a look at the ratio, so we have 1 mole of hydrogen gas, and we also have 1 mole of magnesium. Okay, so it's a 1-to-1 ratio. So basically, the number of moles for hydrogen will be equal to the number of moles for magnesium, which is 0.0025. All right, so now we can go and say number of mole is equal to the molar mass, the mass over the molar mass. All right, so if I wanted the mass, I would multiply it. I would get it by multiplying number of moles and the molar mass. All right, so number of moles 0.0025, and the molar mass for magnesium, let's just have a look at the periodic table. So magnesium is 24. I hope you can see that. Second group, third period. So there's magnesium, 24 grams per mole. Okay, coming back to our question over here. So there we go, 0.025, multiply that by 24, and we get 0.06 grams. Okay, and yeah, so that is the magnesium that has been used up. Now they asked us to calculate the mass of magnesium that remains. Okay, so the mass of magnesium that remains, initially we had a mass of 2 grams. So 2 minus 0.06. Okay, 2 minus the answer, and that is 1.94 grams. And that's basically that. For how many marks? 5 marks. Yeah. I think it was worth the 5 marks. Okay, and then 5.7. It says medication used to relieve headaches is available as powders or tablets. Use the collision theory to explain why powders provide faster relief than tablets. Okay, that's for 2 marks. Well, basically, with powder, you have a bigger surface area, okay, as opposed to the pills or the tablets. Okay, so with powder, you have an increased surface area, all right? Therefore, there are more contact sites. Okay, than you would get with the tablets. Okay, now what does that mean then? Therefore, that means that you will have more effective collisions. Okay, per unit time. All right, and that helps in relieving the headache quicker. So yeah, that is it for question 5. Question 6. Hydrogen gas is prepared by the reaction of methane and steam, as shown in the following balanced chemical equation. So we see that this reaction has a positive enthalpy, meaning that the forward reaction is endothermic while the reverse is exothermic. So the methane and steam are sealed in a 2 cubic decimeter container to react and are allowed to reach equilibrium at temperature T. So 6.1, state Le Chatelier's principle. All right, so this is part of the theory that you need to learn. And basically, Le Chatelier says, once you have reached equilibrium and something disturbs that equilibrium in a closed system, then the system will try to reinstate a new equilibrium, all right, by favoring the reaction that will oppose the disturbance. Okay, I hope that's clear enough. Now the methane and, okay, no, I've already read that, 6.2. Use Le Chatelier's principle to explain how the following changes will affect the yield of hydrogen gas. So 6.2.1, if we add more of methane, all right, so if we increase the reactants, what does Le Chatelier say? It says that to oppose that disturbance, we also need to now increase the products. All right, so increasing or adding more of methane will rather increase the concentration of methane. All right, and then now the forward reaction will have to be favored, meaning that the products will increase, and as a result, the hydrogen will increase, so the yield will increase. Okay, so for 3 marks, how am I going to write that properly? Okay, I will say that, okay, by adding more of methane, then I would increase the concentration of the methane, then the forward reaction will be favored as a result. Okay, and therefore the yield of hydrogen gas will increase. And then 6.2.2, a decrease in the volume of the container. So when you decrease volume, first of all, everything is a gas, right? Yes. If you decrease volume, you are increasing the pressure. And what does an increase in pressure do? An increase in pressure looks at the chemical equation, the balanced chemical equation, okay? And we're going to look at the least amount of moles. Okay, is it on the product side or on the reactant side? So with regard to our reactants, how many moles do we have? We have 2. And with regard to the product, how many moles do we have? We have 4. Okay, so the reactants will actually be favored, and as a result, the yield of hydrogen gas will decrease. Okay, so writing it out properly, I would say an increase in pressure, okay, favors the reaction that produces the least amount of moles. Okay, and what is that reaction that is favored? Therefore, the reverse reaction is favored. Okay, and as a result, therefore the yield, or let me rather put it this way, the yield of hydrogen gas has decreased or will decrease, okay, or decreases. Alrighty, and now it says the sketch graph below shows the changes in the number of moles of methane, steam, and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 cubic decimeter container. So we see on the dependent side, on the y-axis, we have number of moles. On the x-axis, we have time. So now 6.3. It says, write down a reason why there is no change in the number of moles of each of the gases between times 1 and 2. So you see there, the lines are parallel to each other, okay? So that means that you have actually reached equilibrium, all right? And yeah, it's only for 1 mark. So how you would write that nicely, or you could say that the rate of the forward reaction is equal to the rate of the reverse reaction, okay? But you can conclude it and say the reaction is in dynamic equilibrium. Okay, that dynamic is quite important. Dynamic equilibrium. Okay, and what does equilibrium mean? Means the forward reaction is equal to the reverse reaction, or the rate of the forward reaction is equal to the rate of the reverse reaction. But for 1 mark, dynamic equilibrium. In 6.4, it says use the information on the graph and calculate the equilibrium constant for this reaction at temperature T. Ooh, for 7 marks. Remember, the equilibrium constant is the concentration of the products divided by the concentration of reactants. So far, we have information given to us in moles, so we're going to use the Rice table. Okay, and so yeah, let us put in all the reactants and products. Okay, so rice, I'm gonna say rice, and everything is in mole. Okay, all right, but for equilibrium, actually, yeah, anyway, we'll get to that. And then now for the reactants, we have methane, and we also have steam. Okay, and then for your products, we're just gonna draw a thick line. So let's just put in lines there. And then we're going to have it as a double line over here to show that there's a divide between reactants as well as products. Okay, so for the product side, we have carbon monoxide as well as hydrogen. Okay, now in terms of ratios, we have 1 to 1 to 1, but the hydrogen we have 3. Okay, and the initial amount of moles, we are actually given the initial amount of moles. So for the product side, because there aren't any products yet, we'll get 0 and 0. And then for your methane, we have 1,4. For steam, we have 1,2. And then if you look at the graph, at equilibrium, carbon monoxide is actually 0,6. Okay, 0,6 mole. And we know that for the change, so initial, in order to get that change, we're going to add, right, for the products, and we're going to subtract for the reactants. Okay, so we have 0,6. So what plus 0 will give us 0,6. We're going to get 0,6 there. Okay, and then we're going to relate it to the ratios to get the other amounts. So because we have a 1 to 1 for the steam as well as methane, we're going to put 0,6 there. And for hydrogen, it's a 1 to 3. So we need to take 0,6 and multiply it by 3. So that's going to give us 1,8. Okay, now we're going to say what is 1,4 minus 0,6. Let me just put a line there just to show that here we are adding or subtracting. Okay, so now 1,4 minus 0,6, you actually have 0,8. 1,2 minus 0,6, you have 0,6. And yeah, 0 plus 1,8 will be 1,8. And now for us to get the concentration at equilibrium, so equilibrium again, but this time we want the concentration. Remember that concentration is equal to number of moles divided by volume. And we know that the volume here is 2 cubic decimeters. Okay, so for example, for methane, you're going to get 0,8 mole divided by 2, and you're going to get 0,4. 0,6 divided by 2, that will give us 0,3. 0,6 divided by 2 again, 0,3. Okay, let me just write there 0,4 mole per cubic decimeters. And then lastly, 1,8 divided by 2, that's going to give us 0,9. So that's fair enough. We have our concentration. Now we can go back to the Kc formula. Okay, so for our products, because like we said, concentration of products divided by concentration of reactants. So for our products, we have carbon monoxide, and we also have hydrogen, and that will be to the power 3, it's hydrogen gas. And then for our reactants, we have methane. Okay, and we also have steam. Now we're going to take the concentration of carbon monoxide, so that is 0,3. And we have hydrogen, which is 0,9 to the power 3. For methane, we have 0,4. And for steam, we have 0,3. Okay, so if you plug all of that into the calculator, we're going to get 0,3 multiplied by 0,9 to the power 3 divided by 0,4 multiplied by 0,3. And so we have 1,82. And that's just a constant. There's no unit. Okay. And then lastly, 6.5, it says, the temperature T is decreased. How will this change affect the Kc value for the above reaction? All right, so if we have decreased the temperature, remember this reaction is endothermic, okay? So a decrease in temperature means that the reverse reaction is favored. Reverse reaction favored, okay? That is the exothermic reaction is favored. And as a result, Therefore, your reactants are going to increase because they're favored. Okay? And looking at our Kc formula, where we have concentration of products over concentration of reactants. If your reactants are going to increase, remember reactants, or the concentration of reactants, is inversely proportional to Kc, your Kc value. So if your Kc value, or rather if your reactants increase, then your Kc value will decrease. Okay, so if we write down our answer for 1 mark, it will decrease. But this was just me explaining why we say it decreases. And that's the end with question 6. Question 7. The balanced equations below represent the ionization of sulfuric acid in water. Okay, so sulfuric acid is like one of those strong acids like, HCl, which is hydrochloric acid or phosphoric acid, all right? And it takes 2 steps for it to completely ionize. Okay, so yeah, 7.1, it asks, is sulfuric acid a strong or weak acid? Okay, so we've already established that it is a strong acid. And why is that? It's a strong acid because it ionizes completely. Ionizes completely. All right. And then 7.2. Write down the formulae of the conjugate acid-base pairs in step 2. Okay, so in step 2, HSO4 is actually an acid, and H2O then, in this case being an amphelite, this case is a base. Okay, now H3O, we know that that's an acid. Okay, hydronium, so that would be your conjugate acid. So H3O, that's your conjugate acid. It goes along with H2O. All right, and then SO4, 2 minus, will then have to be your conjugate base. All right, so it goes with it goes with HSO4. Okay, so yeah, those are the 2 pairs that they're talking about. And then we get to 7.3. So it says, sulfuric acid is diprotic. All right, write down the meaning of the term diprotic. Yes, it is. Okay, there are 2 H atoms, so it's diprotic. If you look at hydrochloric acid, it's just HCl, so that is monoprotic. If you have a look at phosphoric acid, it's H3PO4, that is triprotic. Okay, so I hope you're seeing the trend. So what does diprotic then mean in this case? It means that if you have a diprotic acid, it means it's a 2-proton donor. Triprotic would be 3-proton donor, and monoprotic just a 1-proton donor. Okay, so it donates 2 of its hydrogen ions. Okay, or it ionizes to form 2 moles of hydrogen. But yes, so that's the meaning of the term diprotic. And then 7.4, it says write down the formula of the amphelite in the above reaction. So an amphelite is one that can be an acid and a base, all right, or a base. It just depends. So water normally is an amphelite, but in this reaction, so sulfuric acid, let's go to step 1. Sulfuric acid, okay, that is an acid, whereas water is your base, okay, and then H3O, that is your conjugate acid, your hydronium, and HSO4 minus, that is your conjugate base. Now in step 2, your HSO4 minus is actually an acid in this case. All right, whereas your water remains your base. So in this case, it's not acting like an amphiolite, the water. Okay, that's what you would expect, but it is not acting as an amphiolite. And then you have your conjugate acid, which is H3O plus, your hydronium, and you have the naked SO4 without the H's. That's your conjugate base. So you can see here that water will not be your amphiolite, but HSO4, because once it was a base and then became an acid. All right, so what is the formula of the amphiolite? It is H. So our answer would be HSO4 minus. Okay, and then 7.5. It says an impure sample of potassium hydroxide pellets with a mass of 11.2 grams is added to 0.09 mole of sulfuric acid with a volume of 600 cubic centimeters. It reacts according to the balanced chemical equation given below. So you have a strong acid, sulfuric acid, and a strong base, potassium hydroxide. All right, so you produce a salt and water. Okay, potassium sulfate as well as water. Now 7.5.1 says calculate the initial pH of the sulfuric acid used in this reaction. Okay, remember the formula for pH? If you have forgotten it, it's there in the formula sheet, but pH is negative log H3O. Okay, so basically we're looking for the concentration of hydronium. And we can actually relate it to sulfuric acid because remember sulfuric acid is diprotic. Okay, so I know that once I have the number of mole for sulfuric acid, I can relate them to the number of mole of hydronium. And because sulfuric acid is diprotic, it will produce, you'll have that ratio of 1:2. So let's go ahead and get the number of moles for, or not even the number of moles, we can get the concentration of sulfuric acid, because that will relate to the concentration of hydronium. Okay, so concentration is equal to number of moles over volume. And in this case, we have 0.09 mole. Okay, so let me just put it like this: concentration of sulfuric acid, H2SO4. Okay, so number of mole here would be 0.09 divided by the volume, which is 600 cubic centimeters. We're going to divide that by 1,000 so that we can get cubic decimeters. Okay, so 0.6 cubic decimeters. All right, and then when we calculate what the concentration is, we get 0.09 divided by 0.6, and we get 0.15 mole per cubic decimeters. Okay, so that helps us. So now we know the concentration of sulfuric acid. Okay, H2SO4. We know that it relates to twice that of hydronium. Or rather, let me put it this way. In order for us to get the concentration of hydronium, it will have to be twice the concentration of sulfuric acid. Therefore, the concentration of hydronium is 2 times 0.15, which is 0.3 mole per cubic decimeters. Now we can go ahead and calculate pH finally. So pH, negative log of H3O, our hydronium. So we have negative log times 0.3, and let's just use our calculator. So negative log times 0.3, and that is equal to 0.52. That tells you how acidic or strongly acidic it is. It's close to 0. All right, now 7.5.2. Now it says the percentage purity of potassium hydroxide pellets used is 80%. Remember they told us that the mass of your potassium hydroxide pellets is 11.2 grams. Now they're telling us that 80% of it is actually pure. Now calculate the number of moles of pure potassium hydroxide that reacts with sulfuric acid. So I'm just going to determine what the mass is for 80% of potassium hydroxide, or the pure, let me rather say the mass of the pure potassium hydroxide. Okay, so that's 0.8 multiplied by 11.2. So 0.8 multiplied by 11.2, and that's equal to 8.96 grams. Now they want the number of moles. Okay, number of moles is equal to mass over molar mass. All right, our mass is 8.96 grams, and the molar mass for potassium hydroxide, so potassium, oxygen, I know hydrogen is 1, oxygen is 16. I don't know about potassium. Let's go check it out. So it's in group 1. Potassium is 39. Okay, so 39 plus 1, that's 40. And 40 plus 16, that is 56. Okay, so we have a molar mass of 56 grams per mole. Okay, so now if I take 8.96 and I divide it by 56, I get a value of 0.16 mole of pure potassium hydroxide, right? So they want us to calculate number of moles that react. So this are the number of moles that react with sulfuric acid. Now the last question. It says, determine which reactant is in excess and hence state whether the final solution is acidic, basic, or neutral. So we have 0.16 mole, all right, of potassium hydroxide that reacts with sulfuric acid. And if we have a look at our equation, we actually have 2 moles. Well, the ratio. So if you have potassium hydroxide and you have sulfuric acid, we have 2 mole for potassium hydroxide and 1 for sulfuric acid. So basically 0.16 mole of potassium hydroxide actually reacts, whereas 0.08 mole of sulfuric acid will react. But how much did we have for sulfuric acid initially? We had 0.15 mole. No, that's the concentration. We had 0.09 mole initially. Okay, so basically we have only 0.01 mole left over. And we've used up all of the potassium hydroxide. Therefore, we can conclude that the reactant that is in excess is basically acidic. Okay, because we have excess sulfuric acid. All right. And that is it for question 7. question 8, the second last question. All right, so it says a galvanic cell is set up using a manganese rod and an unknown metal. Okay, so galvanic cell, meaning you have a salt bridge, it's that one, or voltaic cell. The initial EMF measured under standard conditions is 1,05 volts. It is quite important that it is a positive value, okay? If you were to measure the EMF and find it to be negative, you're not dealing with a galvanic cell, you're dealing with an electrolytic cell. So just be careful of that. The electrons flow from manganese, that's very important, to metal X in the external circuit. So electrons always flow from the anode to the cathode. So that tells you something. Alrighty, now let's get to answering questions. So 8.1. Is the reaction that occurs in the cell spontaneous? Yes. With galvanic cells, galvanic or voltaic cell, the reaction that occurs is spontaneous. And now it says give a reason for the answer. Okay, so it is spontaneous because the EMF is greater than 0. Or we could say the EMF is positive. Okay, and then 8.2, it says which electrode, X or manganese, is the anode. Remember, they said electrons flow from manganese to metal X. So wherever it's flowing from, that's the anode, and where it's flowing to is the cathode. So X is the cathode, and manganese is the anode. Okay, so you can just say Mn or manganese. 8.3, use calculations to identify metal X. Okay, so we're gonna, for 5 marks, we're gonna look at the formula sheet. So we can then say E cell, don't forget that, is equal to E cathode. Please write the full cathode out. If you just say EC, they're gonna subtract marks from what I've heard. Okay, so we already know what the E cell is, which is 1,05. And we already know that at the anode we have manganese. Okay, we don't know at the cathode. So for manganese, we're just going to go to the table of standard reduction potentials. You guys are used, most of you are used to table 4B. So let's go have a look for manganese, and I see it right there. Okay, so there's manganese, and we have negative 1,18. All right, so what is the reading for the cathode? So we're going to say 1,05 minus 1,18. I hope you see it, because we're going to have, 1,05 minus 1,18, because that negative times a negative gives you a positive. If you take it to the other side, it has to be a negative. All right, and we get negative 0,13. And don't forget the unit, volts. So if we have a look, where do we get negative 0,13? Negative 0,13 is actually lead. Okay, therefore X is equal to lead. Alrighty, this question is going by fairly quickly, or am I in a rush? I actually kind of am in a rush. I'm hungry. So I just want to finish recording this and then go and eat. All right, 8.4. Yeah, so that was for 5 marks. They were being very generous. In other papers, that probably would have been 3 marks. But yeah, I guess they were being very generous. Now, 8.4 says, for the cell, write down the 8.4.1, 2 standard conditions. Okay, so standard conditions, that's why we have the E note there. The note just says standard. Okay, standard conditions. Well, we would have to refer to temperature and concentration, okay, not pressure in this time around. So when it comes to temperature, what are we expecting? 25 degrees, so you can convert that to Kelvin, okay, 25 degrees Celsius. And concentration, basically that would have to be 1 mole per cubic decimeters. And then 8.4.2, write down the cell notation, okay, the entire cell notation. Remember, we start with the anode, okay, everything to do with the anode. Then we have our salt bridge, and then we have everything to do with the cathode. So in our anode, we know that we have manganese, okay, so we have the anode for manganese, which is a solid, all right, and then we have our electrolyte, so we're going to have the aqueous, okay. If you're not sure really how it dissociates, so where's manganese again? So we're going to have Mn 2 plus, and that's an aqueous solution, okay. And in that case, I don't know how strict they are, but you could say the concentration there is 1 mole per cubic decimeters. Then you have your salt bridge, okay. Then you have the lead. There's the lead, that is in solution, so we have the ions there, okay, with a concentration of 1 mole per cubic decimeters. And then we have our lead cathode there, okay, the solid, okay. So yeah, that is basically it. That's the cell notation. Your electrode, yeah, I wanted to say your lead electrode, okay. So where are we? Yeah, that's the cell notation for 2 marks. And then lastly, 8.4.3, it says write down the reduction half reaction. Remember, at the anode, that is where oxidation occurs, and then at the cathode, that is where reduction occurs. So red cat, actually, that's what I wanted to write. So reduction occurs at the cathode. So we are basically focused then on we're basically then focused on what's happening at the cathode, all right. And with the reduction half reaction, the way they present it in the table of standard reduction potentials is basically you're going to write it as it is, okay. If it's on the cathode side, you write it exactly as it is. If it is on the anode, you swap it around, okay. So the half reaction then becomes lead, the aqueous solution, okay, plus 2 electrons and 1 arrow. Please do not put the double arrow. It's not reversible. So yes, we have that, and then we're gonna get the lead solid. All right, and I believe this is it for question 8. It was short and sweet, and that is great, and 14 marks, which is quite nice. So yeah, see you question 9. Question 9. This is the last question for the chemistry paper. And yeah, please don't forget to like our videos and also subscribe to our channel. If our channel has been of good service to you, please don't keep this information to yourself. Tell a friend, fellow matric student, or those doing matric next year. All right, so it says the diagram below represents the purification of copper ore to pure copper. The cell also contains zinc, silver, and platinum impurities. Okay, so having a look at our electrodes, we know that in an electrolytic cell, the electrons flow from the positive terminal to the negative terminal. So we can say or conclude that A is our anode and B is our cathode. Okay, at the anode, that is where oxidation occurs. At the cathode, that is where reduction occurs. Okay, so the graph shows the initial relationship between the mass of copper deposited versus time. So it's quite a linear relationship, okay, and it is directly proportional. So with time, you get more copper that is deposited. Now coming to the questions. 9.1, write down the energy conversion that takes place in the cell. So with an electrolytic cell, which is opposite to a voltaic cell, you actually have electrical energy. Okay, energy conversion is from electrical to chemical energy. And then 9.2, at which electrode, A or B, would pure copper be deposited? Okay, so again, looking at our diagram over here, at A, that is where oxidation occurs, all right? So you'll be losing some mass there. And B, that is where reduction occurs. So that's where the copper, the pure copper, would be deposited. Okay, so 9.2 is B. 9.3, write down the half reaction that takes place at the anode. All right, so whatever takes place at the anode, remember we're going to swap what is given on the table around. Okay, so let's go look for copper. Copper 2 plus. Okay. So not this one where it's copper 2 plus with 1 electron. We need copper 2 plus with 2 electrons. Okay, so you see the way they wrote it? We have positive 0.34. You are going to swap it around because we have our copper solid there. Okay, the electrode. And then with one arrow, then you're going to have copper 2 plus 2 electrons. Okay, and that is the half reaction that takes place at the anode. Okay, quite blurry. Let's wait for it to come back to normal. All right, so that's 9.3. 9.4, how will the gradient of the graph be affected as the reaction is allowed to proceed until completion? We're not expecting any change. This graph will remain as it is, okay? And once it's complete, it still remains as it is, okay? So in this case, it remains the same. It's not like a rate of reaction graph where once it reaches equilibrium, it now is parallel to the x-axis. Okay, then 9.5. Refer to the relative strengths of reducing agents to explain why zinc will not be deposited at the cathode. So why will zinc not be deposited whereas copper is? Let's go to our table of standard reduction potentials, table 4b. Where is copper and where is zinc? So if I look from the top, by the way, as you go up, we have increasing reducing ability, okay? Meaning we are increasing, like the reducing agent gets stronger as you move up the table. All right, so zinc, I can see this is where zinc is, okay? So zinc, it's pretty much above copper. So we have zinc at the top and copper somewhere at the bottom here, yes. Okay, because copper we have plus 0.34, zinc we have negative, let me just check again, negative 0.76 volts. Ooh. Okay, so then in this case, because zinc, okay, so zinc is the stronger reducing agent. Between itself and copper, it will not be reduced. Okay, copper on the other hand is, or rather copper will be reduced. Okay, so basically the stronger reducing agent is zinc, and it will not be reduced. Not be reduced at the cathode. Copper on the other side, the copper 2 plus ions will be reduced to the copper metal, okay, at the cathode. So zinc is not really a threat to copper, okay. So yeah, basically copper 2 plus is a strong oxidizing agent, meaning that is the one that it will be more likely to be reduced, whereas zinc is a weaker oxidizing agent and will not be reduced to deposit on the cathode. Okay, so rather zinc will be oxidized to get zinc 2 plus ions, whereas copper 2 plus will be reduced to get copper metal at the cathode. All right, so that was 9.5. And now 9.6, the last question. So 9.6 says, when the current flows for 30 minutes, 15 grams of pure copper was deposited at one of the electrodes. Okay, so we know that it is the cathode. Now it says, calculate the number of moles of copper that was deposited. Okay, so number of moles for copper is basically the mass over the molar mass. So the mass they told us about is 15 grams. And if we have a look at the periodic table, copper, which is somewhere in between, there we have 63,5 grams per mole. So now the number of mole that we get, it's 15 divided by 63,5, and that is 0.24 mole. Okay, let's go back to our question. Now the absolutely last question, and that was 3 marks. Okay, 9.6.2, determine the number of moles of electrons that flow through the circuit while 15 grams of copper is being deposited. Okay, so every mole, 1 mole of copper, you actually have 2 moles of an electron. And how do I know that? If we have a look at our formula over here, so we have 1 mole for copper and 2 moles for the electrons. Okay, so if copper, I had 0.24 mole, it means that the number of moles for the electrons will actually be twice 0.24. Okay, so I'm going to take my answer, multiply it by 2, and we get 0.47 mole of electron. Okay, and that is basically the whole paper. All right, I hope you've learned a thing or two and you can be able to apply it as you are preparing for your final exams.